Good morning, welcome to new lecture. In this lecture, I will solve different examples, but first I will look at one bar, rod or bar. It is hanging from the ceiling, and the only external load we have here, it is self-weight. So we have one rod. It is, for example, assume the cross-sectional area, it is constant throughout this bar. So the cross-sectional area, it is constant. We have one bar or rod. The length for this bar, it is L. The cross-sectional area, it is A. We fix this to the ceiling and it is hanging, suspending. Only the external load we have on this bar, it is self-weight. We don't have any other external load. We want to find what is the deformation for this rod. If we have one rod, it is hanging with self-weight. What will be the deformation of this rod because of that self-weight? This entire self-weight, for example, it is W, and the Young modulus, it is E. So what is the problem statement? Problem statements is this. We should find the deformation of this rod. And this rod, it is hanging from ceiling, and the only external load we have, it is self-weight. Entire weight of the rod, we assume it is capital W, which is known. Young modulus, it is E. The length for this rod, it is L, and the cross-sectional area is A, and the cross-sectional area is constant in this bar or rod. If it is not constant, we should modify the solution. That will be another problem. Again, I will solve it. But for now, we know these are known value. We want to find the deformation for here, deformation for point 1, which is, you see the location of the point 1. It is in free end here, and then I will find another deformation maybe at point 2 location. It is in L over 2 from support. Let's first find delta 1. If we have a rod and it is hanging from ceiling and the only external load we have self-weight, what will be deformation in the free end? If you remember deformation formula, if we have rods, that rod is subjected to external load. For example, we have the same rod, but instead of self-weight is subjected to external load F at free end. In that case, deformation, it is, we prove it FL over EA. But now we don't have this external load. Instead of that, we have self-weight. Self-weight W, it varies from the free end until the supports. For example, if here in this example, if I cut this bar in any section perpendicular to the bar, any section, for example this, what is the internal force in the bar? It is F. If I cut here, what is the internal force in the bar? Again, it is F. If I cut here, if I look at to this as a free body diagram, what is the internal force in the F? It is again F. If I apply F at free end, in any section I cut this bar, internal force, if I draw free body diagram 1, free body diagram 2, free body diagram 3, and so on. In any section, if I cut this bar perpendicular to the bar and I draw free body diagram, internal force will be equal to the external load, because summation of forces in vertical direction should be equal to 0. But once it is hanging under self-weight and we don't have external load, what is happening? This is problem a little bit is different. Why? Because if we look at this example, entire weight is W. But if I cut here at section 1 and look at this free body diagram, I cut a piece of this, for example, in x1 distance from free end. So the weight is effective on top segment. It is the weight of this part. So if the weight of this part is W, the internal force, the weight of this W will be like external force for remaining bar. So here we have W1. But if I cut here at section 2, I cut at the distance of x2 from free end. Now, for this part, the weight of this segment acts like external load. So here we have weight W2. So from free end to top to the support, if I move from free end to the support, weight step by step will increase. In the beginning, if I cut, I will cut very close to the free end, and that weight it is close to the zero. So in the beginning, if this is length L, if I cut here, the weight of only these parts, which I show with W1, acts as an external load for this part of the bar. But if I cut far from free end, for example, here, the weight of this part acts like external load here. So here, this is W1, this part is W2, and W2 is much bigger than W1. And finally, very close to the support, the weight, it is total rod weight, and it is equal to the W. So here in this formula, F, it is not constant anymore. It varies from 0 to W. So how we will solve this problem? In order to solve this problem, we should modify this formula, because external load is function of the location we are cutting. So it will be integration of Fx dx over Ea. E-Young modulus, it is constant number, it is not function. In this example, cross-sectional area is constant, so it is not function of the x, the location of the cut. But the external load will be function of cut point. So I assume I cut this at x distance from free end. What is the weight? Weight is unit weight times volume. Here, if I cut in x distance, what is the weight for this segment? What is the weight for that? It will be unit weight times the volume Vx at x location. So it will be unit weight times volume is cross-sectional area times length. Length over there it is x. So now the remaining part is like this, and here external load is gamma Ax. It varies from x is equal to 0 up to L. So I can write delta is equal to integration of gamma Ax divided by Ea from 0 to L dx. Instead of Fx, I plug this gamma Ax dx Ea, because why? because here, if I cut at x distance from free end and I assume one small element, the small element length is dx. The weight for this part, which is gamma ax, gamma is unit weight, times the volume will be weight for this part, this segment. Okay? That weight acts similar to external load for this element. This element length is dx divided by EA. So instead of Fx, I will put gamma AX dx over EA. From here, you know A and A, they can cancel each other. Gamma over E, it is constant, so I can pull out of integration from 0 to L x dx. If I integrate this, this is very simple. It will be gamma, I write all the steps. It will be gamma x squared over 2e from 0 to L. This will be gamma L squared over 2e. Now, so the delta for point 1, entire deformation, will be gamma L squared over 2e. If I multiply this by A over A, I can do that because A over A it is 1. I can write this gamma A L squared over 2E A. I can write this like this, gamma L, gamma AL times L over 2E A. Gamma times A times L. A times L will be volume. Gamma times volume will be total weight. So this part, it is total weight. So I can write total weight times L over 2EA. So deformation of the one rod. If that rod is hanging under only self weight, will be equal to entire weight W times the initial length L over 2EA. And pay attention, the cross-sectional area is constant in this rod. So this will be deformation for point 1. What does that mean? If I want to express that in another form, see what is happening. If I have this rod, instead of W weight, I assume it is weightless. And I apply the external load W. I apply the self weight W as external load at the end point, point 1. What will be deformation? In that case, deformation for point 1 will be WL over EA. So if I apply entire weight, at the end will be WL over EA. But if it is hanging under self weight, it will be WL over 2EA, half of that. So I can model this. Instead of self weight, it is hanging under half of total weight. Okay, we apply that for total weight as an external load at the end. So if I make this instead of total weight W, half of total weight, it is W over 2. Here I can put instead of W over 2 times L over EA, which is equal WL over 2EA. We will have the same answer. Now, what will be deformation at midpoint? If we have the same rod, it is hanging under self weight, we calculated the free end deformation, it is WL over 2EA, and W it is entire weight. How about deformation at point 2? Point 2 it is L over 2 from top and L over 2 from the free end. So what is the deformation for delta 2? So if delta 2 initially it is here, deformation here is initially it is 0. After applying the self weight, that point 2 will come down. How much it will deform? What is the delta 2 deformation? How much this point under self weight will move down, which we call it delta 2. So let's explain one more time. Delta 1, first we have this rod, the young one just it is E, cross-sectional area it is A, the length is L, total weight is W. Before we hanging under self weight, the length is L. After hanging under self weight, we will have deformation here. Point 1 will move down, point 1 prime. That will be our delta 1 deformation. But point 2 here, L over 2, will move down to how much? Delta 2. I want to calculate that. How I can calculate that? That is again easy to do it because we can use the result of delta 1. Result of delta 1, how we can use it? I can separate this problem to two problems. One of them I cut at middle here is L over 2. If I cut at middle, this piece, this segment I'm cutting, I'm separating. What is the weight for this segment? This weight segment, if total weight is W, the weight for this segment, it will be what? W over 2. So that weight will be similar to external load at point 2. So what is that? W over 2. Still, this part has a self weight. How much the self weight for that part? The self weight for that part, it is W over 2 because we cut half of that, we separated, the weight is W over 2, I apply here. The remaining weight again for here, it is W over 2. I apply half of that at end point, point 2. So W over 2 times 1 over 2, W over 2 will be W over 4. What is the length for this? It is L over 2. So delta 2 will be equal to, delta 2 will have two parts. Deformation at part 2, one portion comes because of the weight of this part. That deformation is weight of that part, W over 2, times the length, it is effective in this length, L over 2 over EA, plus another part comes from self weight of this part. The self weight of this part, it is W over 2. The self weight instead of W is equal to W over 2. The length for top part, it is L over 2 divided by, here if it is self weight, 2EA, or if we apply as external load, half of W over 2, W over 4 times L over 2 over 2EA. Both, it is the same. So from here we will have W L over 4 EI plus W L over 8 EA. Sorry, this is EA, not EI. EA. So delta 2 will be equal to 8EA. This will be 2WL plus WL will be 3WL over 8EA. So if I summarize everything one more time, what we will have, let's summarize everything one more time. If I have one bar is hanging from ceiling under only self weight, the length for this bar, it is L, the Young modulus, it is E, cross-sectional area, it is A, and it is constant in entire rod. Total weight for this rod is W. What will be elongation of this rod? Elongation of this rod or deformation at point 1 will be equal to total weight times length divided by 2EA. 2EA. Why? Because in other problem we had, we assume in all of them the rod is weightless. We neglect the weight of the rod, and always they were subjected to external load, something like F. And in that case we had FL over EA. But F is constant in entire this rod. If I apply F here, if I cut in this location, in this location, in this location, in this location, in any location, internal force will be equal to this F. So internal force is constant. So in that case it is FL over EA. But if it is hanging under self weight, it is not same behavior. The behavior will be totally different. If I cut here, the weight of this part is hanging from top part. If I cut here, the weight of this part, it acts like external load, and the weight of this part is hanging from top part. You see, from free end to the support, the weight or external load is increasing, but the length of the rod is decreasing, because here the weight is this much, the length is this much. If I cut here, the weight is this much, but the length is this much. So once it varies, we should take one small element. So once it varies, I should cut in X distance from free end, and in that case what will be the force on this element dx? The force will be weight of this piece times the length of the dx divided by EA. If I integrate it from z, because x is varies from 0 to L, if I integrate it from 0 to L, I will end up with this answer. Now, what will be the formation at point 2, middle of this rod, at L over 2, at middle of this rod, if I cut it, I have the self weight of this part acts similar external load to this length. I have the formation of point 2 because of this external load, plus still I have the formation because of self weight of top part. And the self weight in that case for top part, it is W over 2. So the total deformation delta 2 will be equal to W over 2 times L over 2 over EA, because the weight of this part, it is similar to external load to top part. That is because of the force or external load times the length divided by EA. Plus, still we have deformation at point 2 because of the self-weight of top part. That will be the top part self-weight, it is W over 2 times the length, L over 2, divided, because this is deformation because of self-weight, divided by 2EA. This will be, finally, it was 3 over 8 WL over EA. Let's double check. I see everything is right. Yes. So at free end will be WL over 2EA. At midpoint will be 3WL over 8EA. Thank you so much for watching this lecture. See you next session.